Chapter 6, Rational Exponents and Radical Functions. Sections 6.1 and 6.2, nth roots and rational exponents. So this is read b to the nth power equals a, and it means the same thing as b equals the nth root of a. So for example, if we have 4 to the third equals 64, that means the same thing as 4 is the cubed root of 64. There's various properties to remember about taking roots, and one of them is depending on whether we're dealing with an even root or an odd root. So realize that what it means to take a root is we're finding how many numbers, what number multiplies a certain number of times together to get the inside number. So when we're dealing with the square root of 4, we're dealing with an index of 2, meaning we're looking for two of the same number that multiply together to give me negative 4. This is not possible. So therefore, when the number inside an even root is negative, there are no real nth roots. If we're taking the square root of 0, well, 0 times 0 is 0, so there's only going to be one root. And then again, if we're dealing with a positive number, for example, the square root of 4, we're looking for what number multiplies by itself to give me 4. And that's going to be 2 or negative 2, because 2 times 2 is 4, negative 2 times negative 2 is 4. So it's very important that you remember that when you're dealing with an even root, there will always be two answers. If we're dealing with an odd root, on the other hand, for example, the cubed root of 8, we're looking for what number multiplied by itself 3 times will give me a negative 8. So negative 2 times negative 2 is positive 4, times negative 2 gives me a negative 8. So there will be one answer. The cubed root of 0, of course, is 0. And the cubed root of positive 8, I'm looking for a number that multiplies together 3 times to give me a positive 8. So it will be 2. So in other words, whenever you're dealing with an odd root, there will always be one answer. Properties of rational exponents. So the nth root of a, I'm just writing this a little bigger, the index is going to be the denominator of my rational exponent. And so when we look at this next example, if I were to have the nth root of a to the m, well, I have my a to the m, and then my root becomes a rational power, so 1 over n. Remembering the properties of exponents, I can multiply my exponents together, and I get a to the m over n. And then just another reminder that when we deal with negative exponents, even if it's a fractional or rational exponent, that still means that we move it to the denominator. And just a reminder that if you have a negative exponent on the denominator, then it means to move it to the top. So let's rewrite some of these to the other form. In this first example, the 3 is the denominator, so that's going to be the root, and we're going to have the x squared on the inside. Keep in mind, you could also write this as the cubed root of x and then make it squared. For the next example, you need to remember or realize, actually, that the y to the 5/4, the exponent is only on the y. It's not an exponent raised on the 3 as well. So again, the 4 is my denominator, so that's going to be my index, and then I have y to the 5th. The last one, the 3a is all of that inside the radical, so that's going to be 3a to the 1/4, and then of course I'm raising that to the 5th. When we multiply our exponents, we're going to get 3a to the 5/4, and then again, using properties of exponents, I could expand this slightly farther, 3 to the 5/4, a to the 5/4. Let's evaluate some of these expressions and show our work, and then we can check it with our calculator. So 16 to the 5/2, the denominator of 2 means we're dealing with the square root of 16, and then we're going to raise that answer to the 5th power. So the square root of 16, hopefully you realize, is 4. 4 raised to the 5th power is going to be 1024. In the next example, don't forget to take care of the negative exponent first. So the first thing we're going to do is move that to the denominator. Then if we rewrite this, again, my denominator is 3, so I'm dealing with the cubed root of 64, and then I need to square that answer. The cubed root of 64 is 4, and I still need to square that answer, and so my answer is 1/16. I will not want decimal answers for these, so please make sure that you are aware of how to simplify rational exponents so that you can give me fractional answers rather than decimals. And this next one, it doesn't necessarily appear that there's a lot of simplifying I could do, but I could rewrite this so that I have a perfect cubed. The cubed root of 3 to the third would be a perfect cube, but I actually have a 3 to the fourth on the inside, so I need to multiply this by another 3. Remember, I could break up my radicals, and then the cubed root undoes the third power, so I get just 3, but then I still have that cubed root of 3. Problem number 7, it doesn't appear as there's a lot of simplifying I can do, but I could rewrite this with rational exponents. Going back to this last problem real briefly, don't forget that you could check your solutions by plugging both the original problem and your simplified version into your calculator. You should get the same decimal. Now moving on to this problem. We could rewrite it with rational exponents. 6 to the 2/4. I can simplify 2/4 to 1/2, and I could rewrite that as the square root of 6. And again, I could check both the original problem and my simplified version in my calculator, and you should get the same decimal answer. Now let's go ahead and solve some equations. The whole point of solving equations is to get the variable by itself. So what's the first thing we need to do to isolate the variable? We need to divide by the 6, so we're left with x to the 4th equals 625. And again, powers and roots undo each other. Since we're raising to the 4th power, I need to take the 4th root of each side. I'm left with x equals 5. However, remember that we're taking the 4th root, which is an even root, therefore it must be plus or minus 5. Why don't you go ahead and pause the video and do this next problem on your own, and then come back to make sure that we have the right answers. In the meantime, I will silently go through the steps in solving this problem. So you should get y equals 4. And why is it not plus or minus? Because we're taking an odd root, so there's only ever going to be one answer. These next problems look slightly different. Again, we can't just distribute that 3 in, because it's not going to be the same as x cubed plus 1 cubed. If you wanted to expand this, you would have to write x plus 1 times x plus 1 times x plus 1 and FOIL those all out. That would become an awful mess. So let's go ahead and get rid of that 3. Since we're raising x plus 1 to the 3rd power, we can get rid of that by taking the cubed root of both sides. On the left, I'm going to get x plus 1. And on the right, we're going to get into how to do this a little bit later, but I'm going to break up 54 into a perfect cube and a factor. So the cubed root of 27 is 3, and I still have the cubed root of 2. Then I need to subtract 1 from both sides. And so my final answer is going to be x equals -1 plus 3 times the cubed root of 2. Again, this next one, we're going to divide both sides by 2. Why can't we distribute the 2 into the parentheses? I'd like you to think about that and hopefully come to class and be able to give an answer to that. If you don't understand why you can't multiply that 2 in, you for sure should make a note in your note packet and ask about this in class. So then we get y minus 1 to the 4th equals 16. So to get rid of the 4th power, we're going to take the 4th root. Keep in mind that the 4th power and the 4th root undo each other, so we get y minus 1 equals 2. Don't forget that you also have y minus 1 equals -2. You're going to get two distinct answers. You can't just solve one of them, let's say this first one, and then pop a plus or minus onto your final answer. You'll see in a minute that we get two distinct answers. Adding 1 to both sides on the first equation, we get y equals 3. Adding 1 to both sides on the second equation, we get y equals 1. So we have two distinct answers, y equals 1, -1, and y equals 3. So now, this brief review of the properties of exponents. Again, these should be review, and keep in mind that these also apply to all these rational, which means fractional, exponents that we're going to have. If we have the same base, they're both raised to a power. We're simply going to add the exponents. The second one, if we have a power raised to a power, we're going to multiply the exponents. If we have more than one term that's being raised to the power, then all those terms need to be raised to that same power. Keep in mind that they're being multiplied inside the parentheses. If they were being added, then you would have to FOIL, use the FOILing process. A negative exponent simply means to move it to the denominator. So keep in mind again, if it's negative on the denominator, you're going to move it to the numerator. Again, if we have the same base and they're each being raised to a power, then we're going to subtract the exponents. And a over b to the m is going to be the same as a to the m over b to the m. Again, a reminder that these properties also apply to rational and fractional exponents. So, for example, if we have x to the 1/2 times x to the 1/4, if you're not sure what to do, come up with an example with whole numbers. If we had whole numbers, you should know that we're going to add the exponents. So we're going to add the exponents even if they're fractions. The same idea with raising a power to a power. Give yourself an example with whole numbers. If I had y to the third, you would know to multiply those to give me y to the 9th. So I'm going to multiply my exponents. 1/2 times 2/3 is 2/6, and I can simplify that to 1/3. Simplest radical form means to apply all the properties of radicals and remove all perfect nth powers. Like radicals means that radicals have the same index and the same radicand. And so what do those mean? Well, if I have the nth root of xy, n is the index, and whatever's inside the radical is the radicand. In order to simplify radicals, you're going to need to have some sort of familiarity with your perfects lists. We're going to refer to these as. And so my perfect squares is basically 1 times 1, 2 times 2, 3 times 3, 4 times 4, and so on is how you're going to come up with these perfects lists. And so I have this perfects list all the way up to 20 times 20. Keep in mind these are also going to apply to variables. So a to the 2nd is a perfect square because a times a. B to the 10th is a perfect square because b to the 5th times b to the 5th. C to the 18th is c to the 9th times c to the 9th. Similarly, the perfect cubes, 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, 4 times 4 times 4, and so on. And I'm going to have these listed up to 10 times 10 times 10. Again, realizing that a to the 3rd is a times a times a. C to the 18th would be what? C to the 6th times c to the 6th times c to the 6th. So if you want, go ahead and pause the video again and see if you can come up with your perfect fourths and perfect fifths list. Although we don't go as far with either of these lists. So again, 1 times 1 times 1 times 1, all the way up to 10 times 10 times 10 times 10. And again, with those variables. Again, c to the 32nd would be a to the 8th times a to the 8th times a to the 8th times a to the 8th. And then my perfect lists, perfect fifths list, come up with the similar manner. So now let's go ahead and use some of these. First of all, if we were to simplify using the properties of exponents, we're going to add the exponents and get 6 to the 5/6. Rewriting this one so it's a little bit easier to read, I have 7 over 7 to the 1/4. Keep in mind when there's not an exponent written, there actually is that exponent of 1. So when we subtract those exponents, I get 7 to the 3/4. 27 to the 1/3, well, that should maybe ring a bell. That means that we're looking at the cubed root of 27, and we just went over our perfects list, and that's 3. So I could actually rewrite this as 3 times 6 to the 1/4, all squared. Again, keeping in mind that there's actually a 1 on that 3, an exponent of 1. So when I multiply my exponents, I'm going to have 3 squared times 6 to the 2/4. Well, 3 squared I can simplify as 9, and my exponent of 2/4 I can simplify as 1/2. looking at this next example, 64 is not a perfect fourth. If I put this in my calculator, I'm going to get a decimal. I don't want you to give me decimal answers. So you're going to look up at your perfect fourths list, and you're going to ask yourself what number is on that list that divides evenly into 64. And hopefully you know your multiplication facts well enough to see that 16 goes in there. 64 is 16 times 4. I can then break this apart as the fourth root of 16 times the fourth root of 4. The fourth root of 16 is 2, and I can't simplify the fourth root of 4, so that would be my final answer. Similarly with 32, so keep in mind that that is the square root of 32. I'm going to look at my perfect squares. If there's no index written, it's understood that it's 2. 32 is not a perfect square, but the largest perfect square on the list that divides evenly into it is 16. So when I break this apart, I'm going to get the square root of 16 is 4, so it comes out of the radical, and I still have the square root of 2. The cubed root of 81. 81's not on my perfect cube list, but 27 is. So you don't necessarily have to do this step of writing them as two separate radicals. I could look at this and say the cubed root of 27 is 3, and then the 3 is going to stay inside the radical, so I'm going to have 3 times the cubed root of 3. Why don't you go ahead and turn off the video and try to do, or pause the video, and try to do number 18 and see if you can do number 19, and I will silently move through those two examples. One thing I want to bring your attention to is make sure, and this is very important, make sure you always write down what the index is, because we're dealing with a fifth root. If you were to write this answer as this without that index of 5, well, this means you're trying to find the square root of 4, and this is not going to give me this even close to the same decimal approximation. And the next example, I could break up my y to the 9th as y to the 3rd times y to the 3rd times y to the 3rd, and my final answer would be 3 times y to the 3rd. When I'm dealing with my exponents on these variables, I could break them apart into what would be perfects and then the part that would be left over. And so the fourth root of 81 is 3, and the 2 would need to stay inside. The fourth root of x to the 4th is just x, and the x squared would need to stay inside the radical. And similarly, I do this with the y's and the z's, and that would be my final answer. When I'm dealing with the fifth root of 32, okay, I can break it up like this, and then I can take care of all those fifths. The fifth root of 32 is 2. The fifth root of d to the 10th is d squared. D squared, this d squared needs to stay inside the radical. E to the 15th, fifth root of f to the 5th, and then that f squared would need to stay inside, so that again is my final answer. Hopefully by now you're seeing the little trick. I would like you to go ahead and do these last 3 examples and see if you can come up with the right answers, and I again will silently, stealthily walk through them. This very last example is really long, but it's really no harder than any of the others. It just appears to be more difficult because it's so long. And you need to be careful on the last example because it's dealing with a cubed root, and the previous few examples that you've been working on your own were square roots. So again, 72 is 36 times 2. The square root of 36 is 6. The 2 must stay in. Take care of our a's, our b's, and our c's. Go ahead and try that very last example. If you hadn't noticed yet, simplifying the numbers, you're going to have to use your prefix lists. And then the variables, you're going to ask yourself, how many times does the index divide into the exponent? And so if I were to have, for example, the cubed root of e to the 7th, 3 divides into 7 twice. So I would have an e squared that comes out. That would be what I mean by the exponent out. And what's the remainder? When 3 divides into 7, what's the remainder? There's a remainder of 1. So I'm going to have a cubed root of e to the 1st left inside. And that's what I mean by the exponent that's left in. Finally, we're adding like radicals. If you notice in the first example, they're all cubed roots of 9. So we're just going to see how many cubed roots of 9 we have. We have 1 and -2 and 5 of them, so altogether we have 4 cube roots of 9. And this last example, the only like radicals we have are the cube root of 7. So we have, first of all, this 5 times the square root of 7. Then we have 1 and 2 cube roots of 7, so we have 3 cube roots of 7 altogether, minus the 4th root of 7. And that wraps up sections 7.1 and 7.2. Please make sure if you have any questions at all, you bring them to class. That is the whole point of doing this flipped classroom, is so that you have a chance to ask questions. We did cover 2 sections in this video, which is why this video is especially long. They typically will not be this long. So I hope you will go back and review anything. If you're not sure what you didn't understand, then once we go through things in class, then you can go back and re-look at the video if you'd like. Thanks, and we'll see you tomorrow in class.